Hello everyone, today let's take a look at Quantipus number 96, a hard conditional probability question where you're visiting an old friend at her house and she's recently given birth to 2 children. So in each of these scenarios below, what's the probability that both of her children are boys? And more importantly, we're going to figure out the difference between all of these 3 questions because even though they seem like they would all have the same answer, they're all very different. So first of all, what's the probability that she has 2 boys without any conditioning at all? Well, she has 2 children. The first child could have any of 2 genders and the second child as well. So that's just going to be 4 combos of 2 genders. So if we draw out our probability space here, these are our 4 options. We could either get boy, 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 girl, girl, boy, or girl, girl. So all these outcomes are all equally likely. So what's the probability of boy, boy with no condition? Well, it's just obviously going to be 1 on 4. Okay, now let's look at part A, the condition where she tells you that one of her children is a boy. So let's call this event X, and now we're trying to find the probability of boy, boy when we're given X. So how does our sample space get restricted now? Well, obviously we know that this is equal to the probability of boy, boy intersection X divided by the total probability of X. So what is the probability of X? Well, we have a partition up here and we know the law of total probability. So the probability of X is going to be the intersections of X with all of these quadrants. So first of all, if this woman had 2 girls, then what is the probability that she tells you one of the children is a boy? Well, obviously it's going to be 0%. Now, if we're in this quadrant where she has a boy and a girl, what's the probability that she tells you one of her children is a boy? Well, one of her children is a boy, so that happens with 100% probability. Same with these quadrants as well. So the total probability mass of X in this diagram is going to be everything enclosed in this box right here, right? 3/4 of the total probability mass. So the probability of X is equal to 3 on 4, and on top we have the probability of intersection between boy, boy, and X, which is just going to be everything in here, right? Because if she has boy, boy, then she will say that one of her children is a boy 100% of the time. Boy, boy occupies 1/4 of the total mass, so 1/4 on 3/4 is going to give us 1/3. Alright, so now let's move on to part B, where one of her children walks in and it's a boy. So how is this different from part A? Well, let's just look at it here. So let's let Y be the new condition that one of her children walks in and you observe that it's a boy. So then we'd be trying to find the probability of boy, boy given Y now. So if you just follow the exact same process that we did in part A, you'll find the difference, right? Well, we know that this is equal to the probability of boy, boy intersection Y divided by the total probability of Y. So let's find the probability of Y first. We just use the law of total probability like we did in part A. We go quadrant by quadrant and we find the amount of intersection between the event Y and each of these quadrants. So first of all, if this person has 2 girls, then what is the probability that one of her children walks in and it's a boy? Well, obviously it's going to be 0%. So for this quadrant here, we're going to have 0 intersection between Y and GG. So now this is where it gets interesting. Let's move on to this quadrant here where she has 1 boy and 1 girl. So if she has 1 boy and 1 girl, then what is the probability that one of her children walks in and it's a boy? So to put it more formally, we're trying to find the probability of Y given that we're in this boy-girl quadrant here. And this is no longer 100% probability because either of her children could have walked down and half the time it would have been the girl and half the time it would have been the boy. So this is equal to 1/2, not 1, like it was in part A. So in part A, she tells you that one of the children is a boy, so that only rules out this girl-girl case, and all 3 of these scenarios are now equally likely. But in this situation, in part B, we essentially just sampled one of the kids randomly, right? One of the children walked down and it just happened to be a boy, which doesn't happen 100% of the time in these boxes here. 50% of the time a boy would have walked in and 50% of the time a girl would have walked in. So this is what the new green box will look like, representing the probability of Y now. And notice that this condition is more restrictive because we're only encompassing half of boy-girl and half of girl-boy. Also notice that Y fully intersects boy-boy because if she has 2 boys, then the probability that the child who walks in is a boy is going to be 100%, obviously. So all we do is we take this intersection, this highlighted in red, the boy-boy, which we know is equal to 1/4, and we take that over our total probability mass. And then on the bottom, we have the probability of y, which is just equal to the boy-boy section plus 1/2 of the boy-girl section, which makes up 1/4 of the total probability space, plus 1/2 of the girl-boy section, which also makes up 1/4 of the probability space. Again, this is all just basic law of total probability and Bayes' theorem. And this is just equal to 1/4 on 1/2, which we know is equal to 1/2. Also, you could have just looked at this problem and noticed that the random sampling is independent. So if you sample one of the kids and it's a boy, that's completely independent of whether or not the next child is a boy or a girl. But it's just good to go through the whole process and understand the difference between these two conditions in depth. And that'll certainly come in handy in part C, which is definitely the hardest part and the least easy to even intuitively understand. So let Z be the event that one of her children is a boy born on a Tuesday, and now we need to find the probability of 2 boys given this new event. So how could it possibly matter what day of the week a child was born on? How would it be different from part A and part B? Well, let's just go through the exact same process and figure it out again. So again, I have my sample space. I need to restrict it to the cases where Z is true. This is equal to the probability of boy-boy intersection Z divided by the probability of Z. So let's law of total probability go through quadrant by quadrant again and see where Z intersects. So if you have 2 girls, could it possibly be true that one of your children is a boy born on a Tuesday? Well, obviously not, so Z has no intersection with GG again. Now, if she has BG, what are the odds that one of her children is a boy born on a Tuesday? Well, there's only one boy, so he just has a 1/7 chance of being born on a Tuesday. And same for this quadrant up here. There's again a 1/7 chance that this boy is born on a Tuesday. Now for the boy-boy quadrant, what are the odds that one of these children is born on a Tuesday? Well, let's just do some combinatorics real quick. There are 7 possible birthdays of the week for the first boy and 7 for the second boy, so that's 49 total combos. And now if I fix the condition that the first boy is born on a Tuesday, well then I have 7 combos remaining for the second boy. And then if I fix the condition that the second boy has to be born on a Tuesday, then the first boy has 7 combos for his birthday that he could do. So we have 7 plus 7 minus 1. The minus 1 is for the overcounting of the case when both boys were born on a Tuesday, right? Just basic inclusion exclusion. Equals 13 ways that one of the boys is born on a Tuesday. So we have a 13 out of 49 chance that one of the boys is born on a Tuesday for this quadrant here. So 13/49 of this boy-boy quadrant will be intersected with Z, 1/7 down here. I'll try to draw this roughly to scale, so it's going to look something like this, and 1/7 up here as well. So we can say that this is the new area of P of Z. And now let's take the intersection between boy and Z, which is just going to be equal to 1/4. That's the total probability mass that BB takes up. And then we multiply that by 13 on 49. And we take that over the probability of Z. So the probability of Z is just the area of all this green stuff. So it's just going to be equal to 1/4 times 13 on 49 plus 1/4 times 1/7. And actually that again, so we can just multiply this by 2 essentially. Let me make some space down here. So I can cancel out a 1/4 from every term in this equation here, and I'm left with 13 on 49 divided by 13 on 49 plus 2 on 7. Okay, so 2 on 7 is just equal to 14 on 49. So 14 on 49 plus 13 on 49 is going to give us 27 on 49, which will be the denominator for 13 on 49. And this will just be equal to 13 on 27, which will be the final answer for part C. And this is different from the answers that we got in part B, which is different from the answer that we got in part A. So all of these are different questions yielding different probabilities, which is the crazy part, even though they all seem like the same. So in part A, we know that one child is a boy. We don't know which child. We don't know anything about the child. We just know that at least one of our children is a boy. So that only eliminates 1/4 of our probability space. Now in part B, it's different because I've actually sampled one of the children. I know that this specific child is a boy, and that is a stricter condition, so it restricts our probability space more. And then part C, we can intuitively think about it, is that by adding the fact that the child was born on a Tuesday, we're essentially being more specific about the child. That's why this is closer to 1/2 than 1/3. You think about it, for instance, if I had the event instead that one of my children is a boy and they were born on January 3rd, 1935 at the 5th hour on the 30th minute, well, then I'm essentially being as specific as possible without actually saying that this child right here is a boy, right? Because the probability that another child would be born at the exact same time gets really, really small. So this would get way closer to 1/2 as you get more specific.